We know now how to construct a confidence interval for a population proportion, right? And so that gives us a pretty good idea of what the population proportion could be between, right? At least 95 times out of 100, okay? But that still doesn't tell us what it is, right? And so it will forever remain unknown to us. But what we can do is we can at least say, if we make all these confidence intervals, this seems to be a value that's in 95 out of the 100 of them. So let's test it. Let's see, is there enough evidence that the true population proportion is more than this, less than this, not equal to this, right? So we're coming up with some alternative hypothesis. And so we can conduct a test of significance. So that means we need hypotheses, we need test statistic, and we need a p-value, right? And so we're going to go through this step by step and do all that for a test of significance using one sample. Okay, so as you can see here, we have the hypotheses null and alternative, very similar to us. I just want to make sure to point out the fact that PO, this might, formally we call this the hypothesized value of the population proportion. Okay, but this should be really a number. Okay, it should say, if we're flipping a fair coin, we've long known that the proportion of heads of on a fair flip of a fair coin is 1/2, right? But maybe for some reason it's now weighted towards one side, and we're testing. Oh no, it's actually more than that or less than that. So that would be the form of our alternative hypothesis. Okay. Now, before we go on, right, we have hypotheses. Then we typically have conditions that we need to check before we go forward with the calculations, so that we can say, yep, this is actually okay. So we need to check that we have an SRS and your sample size is large enough. And again, large enough here generally means more than 30, unless again you have strong skew or outliers present. If that's the case, look for normality. But if you have skewness, that's not going to be normal. So, but you could have a normal distribution with outliers per se. So make sure to check for those conditions. Okay. And once you do that, then you can calculate your test statistic. Okay. And the test statistic looks a little wonky. But if you think about it, our test statistic was previously for a mean was x bar minus mu over sigma or s, depending on whether it was known or unknown, divided by square root n. And so the square root of n is actually present. Sigma is again changed, just as we saw in our confidence interval margin of error calculation. Okay, and x bar would be our sample or our unbiased estimator. Okay, which is x bar, and then PO is that hypothesized value of the population mean. Okay, so very, very similar. Okay, and so since it is a z test statistic, that means it comes from the standard normal distribution. So then when you're doing in Excel, you would use norm.dist, right? And then you'd enter, your z test statistic, and then you do 0, 1, and then true. And this would, go to the left. And just to be clear, so in the case where we have P bigger than PO for our alternative, whenever we get our normal distribution, right? So we'd have mean 0 here. Maybe this is our z test statistic. When we do this, we would have to go to the right. So in this case, we'd do 1 minus norm.dist. Okay. And then similar for P less than PO, right? We'd have our z test statistic. So mean 0. Maybe our test statistics is over here. So you can get a negative, but then in this case, with less than, you're going under the test statistic and finding that. So that's just norm.dist. And then in the case of two-sided, okay, so P not equal to PO, here would be 0. And then you're looking at your symmetric one. So let's say your test statistic is here. So you're finding that, and then you're finding its symmetric counterpart here, which would be negative z, and finding that. The easiest way I know how to do this would be to do 2 times 1 minus norm.dist. And then make sure when you do this, since you're going to the right, this needs to be positive. So just make sure to do an absolute value. Okay. So that's the easiest way I know how to do it. But if you want to do, make sure it's negative and then, do 2 times that, that's fine too. Okay. But be careful with your p-value calculation as always. Okay. So that's how we do the test. Okay. Now I mentioned in the last video, like, why is it standard normal? Why do we have a proportion? How does it become normal? Here is the idea at a glance. To do this more formally, you need theoretical statistics, which, let me tell you, that's a lot of fun. But the idea is that when we calculate a sample proportion, okay, it's a scaled binomial. And so binomial, we classify that as binomial. Bi means 2, so it's either a success or a failure. So we can classify that as like those having the trait and not having the trait, right? So it's similar to a binomial, but we can't exactly say it's binomial because there's some technicalities there, but it's similar to a binomial distribution. And then when you get a binomial distribution with a large enough sample size, then it's approximately normal. So we're saying, we're doing a bunch of approximating. Under certain conditions, the problems you encounter all meet those conditions. So it's fine for us, but theoretically, there's some details that we need to attend to. And so since our test statistic for one sample z-test was this, we can actually use this form here for our sample, for when we're testing a one sample test for proportions. Okay, so that's why. And the reason, and so for all that, me saying all that, also allows us to use the mean and standard deviation of a binomial distribution. Again, making certain assumptions, it changes the sample mean. So it changes sample mean x bar to p hat, and it changes the population standard deviation from sigma to PO times 1 minus PO. Okay, so when we change things from a proportion to binomial and then to standard normal, that's this is kind of why, at a high level, why this all works. Okay, so if you tuned me out for the last minute and a half or so, that's fine. I get it. Will you be tested on this? No. On that specific bit of knowledge? No. Will you be tested on a one sample test for proportions? Oh, probably. Okay, so we should probably know how to do a test. And here's an example. Okay, same context as we saw in the case of the confidence interval. Now the only piece that is new to us is that this little bit of information has long been estimated that 4% of population of patients in the U.S. Experience one or more health care associated infections, and then so we want to investigate this. Okay, so when we investigate it, right, we're looking for our null and our alternative, right? And so we're saying P, okay, P, and then, okay, we have to define our symbols, right? P is proportion, population proportion of, okay, how can I underline anything? Population proportion of patients in the U.S. that experience one or more healthcare associated infections. For time purposes, I'm not going to write all that out, but I'm just going to say it's all that I underlined in purple. Okay. But so the idea is that previously it was estimated to be 4%. Okay. And then for the alternative, okay, we know we need to compare P to 4%, but is it more than, less than, not equal to? And so it just says, let's see, do the researchers' findings show any significant difference? Well, to me, that's saying not equal. Okay. If you were to do less than, greater than, and it wasn't specific, that would be okay. Okay, because we're still looking, I guess that's still looking for a difference, just a different type of difference. Okay, so there we go. And then with this, we can check our conditions. Do we have an SRS? Well, let's see. So they did, let's see. Do we have an SRS? That is actually problematic here. Do we know that it's an SRS? But so we don't really know that, but we have a large enough sample size So n is much greater than 30. So I'm going to say that's okay. And since it's large enough, SRS is going to be okay here too. But make sure to verify both conditions regardless. Okay. So again, maybe, so if you have concerns about this, this would be an excellent thing to ask. Like, is this an SRS? Well, maybe, maybe not. Should we actually be doing this? So excellent point of discussion. Problems that you encounter independently will likely say this is an SRS. Okay. But here we go. So now we have to go ahead and calculate our test statistics, so Z, right? But for Z, we need to know, we know it's going to be P hat minus PO, and then square root of PO times 1 minus PO all over N. And I want to emphasize too that this is PO and not P hat under here. Okay, that was different with the margin of error calculation. Okay, so P hat, how much is P hat? Well, we actually calculated earlier, it'd be 452 out of 11,282, number of people from the sample with the trait of interest. And then PO is going to be 0.04, okay? And then N was 11,282, okay? So we're going to go back into Excel and calculate this, okay? When I calculate our P value, though, there's a lot of P's floating around. I just want to be clear. What do? I'm going to do 2 times 1 minus norm.dist of the absolute value of Z and then 0, 1, and true because I have a two-sided alternative. Okay, so I need to figure out what Z is over here, take the absolute value of it, and then put in 0, 1 for the population mean and standard deviation since it comes from a standard normal distribution, and I'll add my p-value. Okay, so let's go into Excel and do all that. So I left a lot of my work up here already, and so I'm just going to come back. So I calculated p hat. I just need to maybe introduce PO, and that was 0.04. Okay, and so my test statistic, when I do that, I'm going to do a numerator, I'm going to do a denominator, and then I'm going to go back and fill in the blanks. Numerator was p hat minus PO. Okay, denominator was a square root, SQRT, and then it was PO times 1 minus PO divided by N. Okay, so I get a test statistic like that. And then that's already positive, so I'm just going to do for the p-value 2 times 1 minus norm.dist, and this is going to the right of the p-value, so, or the test statistic. So test statistic, mean 0, standard deviation 1, true, and I get a whopping 97% for p-value. So do I reject or fail to reject? I really hope you say fail to reject. That's a very large p-value. So I would go back here and say p-value is approximately 0.97. So approximately 0.97. And then I would go ahead and conclude. Okay, so I'm going to say since P is approximately 0.97, which is greater than 0.05, which is alpha, we fail to reject the null. And then I'm going to say there is insufficient evidence. Evidence that P, I'm just going to write this in symbols, P is not equal to 0.04. I would write this out in words, just so that I'm acknowledging the context, but I'm trying to save some time because this is a long video, okay? But that's the idea for a one sample test for proportions. Same sort of process, changing some of the mechanics. remember to check the conditions SRS. If it's coming from actual data, from an actual context like this one was, it'll be an SRS. But it's always good to question it and then check that n is greater than 30. Okay, so there we go. Up next, we're going to change from one sample to two sample.